Okay, so we're going to go ahead and talk about geometric series now. And so let's talk about the geometric series. Let's suppose A does not equal 0. Then A is some number where we have A plus A times R plus A times R squared plus A times R cubed, etc., out to A times R to the n minus 1, then R to the n, and so forth. Then this is actually called a geometric series. And actually this series, I'm not going to go show you the proof, but this series, if the absolute value of R is less than 1, then the series converges to the value A over 1 minus R. If the absolute value of R is 1 or greater, then this series actually diverges. So there's a short proof here, but I'm not going to go through that. You can freeze the video and read it if you like. Okay, so here's some examples of a geometric series. So here you have 0.6 plus 0.06 plus 0.006 and so forth. And so what you've got there is you basically have 0.6. You've got 0.6. Let's see. You've got 6 times 0.1 to the nth power is basically what you have here. Okay. And then here is another geometric series, but this one's an alternating geometric series. So it's like you multiply. Let me be more clear over here. So to get from this term to the next term, you multiply by a tenth. And then to get from this term to this term, you multiply by a tenth. So basically you're multiplying by a tenth to go from one term to the next term. Okay, now this one, to get from 2 to minus 2/3, you multiply by negative 1/3. And then to get from minus 2/3 to 2 over 9, you're going to multiply by, you multiply by 1/3, right? Yeah, you multiply by negative 1/3 here to get to this term from 2 to negative 2/3. Then you multiply this by negative 1/3 to get to this term. And then you multiply this by negative 1/3 to get to this, and so forth. And then this one you multiply, you have 5, and then you multiply 5 times 2, then you multiply 5 times 4, then you multiply 5 times 2 to the n minus 1. Okay, so let's determine if we can find out if these geometric series converge or diverge. Okay, so this series, A is 0.6 and R is 0.1. Okay, because to get from 0.6 to 0.06, you multiply by 0.1. To get from 0.06 to 0.06, you multiply by 0.1, and so forth. Well, the absolute value of 0.01 is certainly less than 1. So the series will actually converge to A over 1 minus R. So it would converge to 0.6 over 1 minus 0.1, which is actually 0.6 over 0.9, which is actually 2/3. Okay. Now, this next series, to get from 2 to minus 2/3, you multiply by negative 1/3. To get from minus 2/3 to positive 2/9, you multiply by negative 1/3. To get from 2/9 to minus 2 over 27, you multiply by negative 1/3. Okay, so here R is negative 1/3. So A is 2. In other words, the first term is simply 2, and then R is negative 1/3, and the absolute value of that is certainly less than 1. So the series converges, and it converges to 2 over 1 minus negative 1/3, which would actually be 2 over 1 plus 1/3, which is 2 over 4/3. And then 2 over 4/3 is 2 times 3/4, which would be 3/2. So that series converges to 3/2. Now on this one, a is 5, and then you're actually multiplying by 2 to the first, 2 to the second, 2 to the third, so forth. So you're actually going to get r is actually going to be 2, and since the absolute value of 2 is greater than 1, then the series diverges. If an infinite series converges, then the limit of that nth term must equal 0. Now this only goes one way. So if an infinite series converges, then the limit of the nth term is 0. So here's a series, alright, and it wants us to show that the limit of the nth term, which would be this, is 0. Okay, well, we've already shown that this is the convergent telescoping series. So since we know this series converges, then we know the limit of the nth term as n goes to infinity must equal 0. And obviously you could have easily shown that without using the theorem. But does it go the other way? Can we say that this series converges simply because the limit of its nth term is 0? See, we know the limit of this nth term is 0. Okay, but here's where we have to be careful. This theorem doesn't go the other way. Just because the limit of the nth term is 0, it doesn't mean that the series converges, because the theorem doesn't say that. And actually, if you'll remember, we know that series 1 over n is the divergent harmonic series. So that would have gotten us in trouble if we had tried to take this theorem up here the other direction and tried to say that series converges. We would have gotten it wrong. Okay, so there's going to be a lot of tests for convergence and divergence, but here's your first test. This is the nth term test for divergence. Okay, it says if the limit of the nth term of a series as n goes to infinity does not equal 0, then the infinite series is divergent. Once again, it only goes one way. So if the limit of the nth term does equal 0, it doesn't tell us anything. But if the limit of the nth term does not equal 0, then it does tell us that the series is divergent. Okay? Alright. And actually that's just the contrapositive of the theorem. So let's apply the nth term test and see what we can find out. Okay. So here is a series. Now remember I said just assume these sums go from 1 to infinity. Alright, so here is the series. Okay, let's see. If we took the limit of the nth term as n goes to infinity, you could easily show that the limit of this is simply 1/2. So since the limit of that does not equal 0, the series must diverge. Okay, how about this one? The series 1 over n squared. Okay, let's take the limit of the nth term, 1 over n squared, as n goes to infinity. Oh, that limit does go to 0. Okay, but that doesn't tell us anything. The test doesn't apply here. The test only applies when the limit does not equal 0. So the series may converge or diverge. Okay, same thing here. This limit goes to 0, but the test does not apply. The series may converge or diverge. Okay, now here we've got a little bit different problem here. This is e to the n over n. Okay, now you can actually apply L'Hopital's rule to this, and you could say, okay, the derivative of the top is just going to be e to the n, the derivative of the bottom is going to be 1, and so as n goes to infinity, e to the n goes to infinity. So this limit is infinity. Okay? Alright, but that's not 0, so the theorem just says if the limit of the nth term does not equal 0, then we know the series diverges. So since this is not equal 0, then we know this series must diverge. Okay? The next theorem simply states that if the corresponding terms of two infinite series are identical after a certain term, then both series must either both converge or they both diverge. So what one series does, the other one does. So if the series a sub n and the series b sub n are infinite series such that a sub I equals b sub I for all I greater than some number where k is a positive integer, then both series either converge or both series diverge. Let me do the second one first. It's easier to show. I have this series 1/3 plus a fourth plus a fifth, and that's really just 1 over n plus 2. But actually, remember the divergent harmonic series? If you start at n equal 3, then you would get 1/3, 1/4, 1/5, and so forth. So, since if you go to greater than 3 or greater than 2, then all of these terms will match these terms. Then based on the theorem that we just read, then both of these series must do the same thing. So since we know the harmonic series diverges, then I know that this series must also diverge. Okay. Now let's see what I've got here. Here I've got 1/5 to the 4th power, 1/5 to the 5th power, and so forth. So we're starting at 1/5 to the 4th power. But this one starts at 1/5 to the, if n is 1, 1/5 to the 0 power plus 1/5 to the 1st power plus 1/5 squared. But eventually, if we keep going, we'll get all of these terms. Okay, so all of the terms, so once n is greater than or equal to 5, then all the terms of this series will match the terms of this series. And since we know that this series is actually, this is actually a converging geometric series, and so since this series converges, then the series up here must also converge. Now the next theorem makes sense. It just says if the series a sub n and the series b sub n are convergent series with sums a and b respectively, then the series a sub n plus b sub n must also converge and has sum a plus b. And then this one says if c is a real number, then the series c times a sub n converges and it has the sum c times the series a sub n. And also there's one for the difference. The series a sub n minus b sub n has the sum a minus b. Okay, so if you want to find the sum of this series, basically you just find the sum of this series and the sum of this series and then add them together, and that'll give you the sum. And so I'm going to just move on now to the next theorem. Basically this theorem says that if you have the sum of, if you have a series that's the sum of two series, if either one of those series diverges, then that sum must diverge. So if you take a look at this example, this is the sum of this geometric series which converges plus the harmonic series which diverges. So since the harmonic series diverges, then the sum of these must diverge. Therefore, the original series, which is the sum of these, must be divergent. So that means that, this series must diverge. Okay. Now in the next section we'll actually move on to some more tests for series to determine whether they converge or diverge. So you need to just start gathering these theorems for convergence and divergence, because they're going to begin to add up.